So now when we know what charge tuning is, let's learn how to formulate a charge tuning task as a neural network embedded into the feedback loop. The bigger picture how it's going to work, and I will explain in a great detail later on, is this one. We will measure just a small subset of charge stability diagram. We call them patches. Then we take this patch and input it into a neural network. And the neural network is going to classify the type of transition you see within a patch. You see the 4 options here. Either I have a vertical, or I have a horizontal, or I have both, or maybe I could also have none. That way, if you know what type of transition you have, you can sort of know whether you are in a part of the charge stability diagram in both transitions, only one type of the dot, the other type of the dot, or 0, 0. And then if you navigate through this different type of transitions, you can first arrive to some kind of reference state. This can be 0, 0. And then you can move on through counting the charge transitions to the desired state that you want. Let's look at how this loop looks like in a little bit more detail. So, as I said, first we start just measuring some subset of a charge stability diagram. Let's imagine we already pre-tuned everything, so we are in a double dot regime. We know we have both type of transitions, but now we want to know exactly what kind of charge states corresponds to which voltages. So I just start measure wherever. I give this measurement patch to a feed-forward neural network. Now, this is super similar to what we did in a module 1, except there is one big difference. And the difference is a number of classes that you have. Now, I am just measuring a very, very small square, and I want to know whether within this square I have a no line, horizontal, vertical, or both. So the neural network is similar, but the spirit of what we do is slightly different because we only measure subset. We are not classifying a whole charge stability diagram anymore. And within this subset, we just say one of these 4 options. No line, horizontal, vertical, both. Then if I know which part of charge stability diagram I am in, I can shift my voltages accordingly to the part of the charge stability diagram I want to be in. And then I am going to measure another patch and repeat this whole process. Now we graduated because we already looked at both dense and convolutional neural network. This is again an image analysis that is looking for a specific kind of feature. So by now we know that convolutional neural network is going to be a better candidate for this. And indeed, this is also what you are going to implement in your exercise. But overall, the charge tuning is this kind of loop. Measure a patch, classify, do the next step, measure the patch, and continue until you arrive to a state that you want. What you need to have in mind is that you always need to implement this routine in 2 separate steps. It's useless to me since I'm only classifying what kind of transition I have, but not in which specific charge state I am, to just navigate the states from the state that I don't know which charge state it corresponded to. So what you need to do first is to find a reference state. For obvious reasons, the 0, 0 is a good one for this because you cannot make a mistake by maybe skipping a transition. You just need to be in the part of the charge stability diagram where there are no transition. You could just tune all the voltages super much to the lower value, but you also don't want to be super far away from this lower left corner because then it will take you forever to actually, in a small steps, to get to the charge state you want to be in. So for this state finding 0, 0, you may be fine just measuring relatively big coarse resolved patches and just classifying what kind of transitions you have in those, and it doesn't have to be super precise as long as it lets you quickly arrive to the step 3 here, that is in a part of the charge stability diagram with the state 0, 0. And once you have a state 0, 0, you can repeat the exact same procedure, but now you are going to go the other way. We start at 0, 0, then shift diagonally right. Let's say that our final state is 3, 2 that you see here. So we want to shift diagonally right. We learned that we only cross a one transition, so we shift again and again. And when we arrive to the 3 in the left dot, when we arrive to the 2 in the left dot, we can shift one more to arrive to the 3, and so on and so forth. So basically you find your 0, 0 state, and then you keep shifting your window, and in each window you use your convolutional neural network to classify, and you have to embed this into the workflow where you count the number of transitions sort of manually, because this is the part a neural network is not doing for you. Now I am just telling you about how to classify the transitions, and how to embed it into the actual workflow. That's a separate question that you will get answered in a second. So in your coding demo with Tanko, you are going to do exactly this thing. We give you a charge stability diagrams. You are going to draw a patch. For each patch, you are going to classify what type of transition you have and shift it accordingly. And that way you should get then something like that shifts you to a state 0, 0 eventually. So your drawn out charge stability diagram are going to look something like this. Then you are going to draw a sample windows. This is the example of those 4 labels I explained to you before. Non-transition line, horizontal, vertical, and both. Now, this is a really interesting point to notice, because could you tell the label here just looking at it? Because I couldn't. This is a beautiful thing about machine learning and convolutional neural networks specifically. They are really good at detecting features, and the features are in the data. But maybe just because of the noise and contrast, we cannot see them super well with the naked eye. But even with this level of noise, you will be totally able to build your auto tuner. So okay, we draw the sample windows. We give each sample window to the classifier, and we train this classifier. This is examples of loss and accuracy you should be getting. You see that the accuracy is not 100%, but it will be very, very high. And it can be an extra challenge for you to think about if you can adjust the architecture of your convolutional neural network to make it even higher. And then in a final step, you are going to build a shifter function that lets you navigate through this charge stability diagram. Now, this is not a machine learning thing. You just use the input of your classifier to decide if you want to move diagonally, vertically, or horizontally. And so in the end, in Python, this is just some number of if statements. Tanko will explain you exactly how to formulate them, and then again you can think for yourself if you can come up with a nicer function.